Now it's time to present our next speaker. He is professor and director of the Institute for Metal Forming and Lightweight Components at Dortmund University of Technology in Germany. The title of his presentation is Flexibility in Forming, New Technologies at IUL. I'm happy to give the floor to Professor Dr. A.Erman Tekkaya.
Thank you very much for this kind introduction. Ladies and gentlemen, good morning. I'm very honored to be at this very important conference, which is extremely well organized. I would like to start to share with you my screen, and I hope we test that several times, and it should work well. So sorry. I hope you can see my screen now. Could I have a feedback whether you see it? Yeah, thank you very much. So my co-author is Mr. Alexander Schoftiak, who assisted me to prepare this talk, and we have several contributors who are mentioned at the bottom here, who contributed with their different works. The title of my talk is Flexibility in Forming, New Technologies at the IUL. IUL is the Institute of Forming Technology and Lightweight Components at the Technical University of Dortmund. And you see here several screenshots of one of the halls of our lab, and you see that we have several industrial scale equipment here and also in the other halls which are available. So I would like to start with an attempt of the definition of flexibility, and for that purpose I would like to use the keynote paper which has been presented at the CRP in the year 2018, headed by Professor Yang from the KAIST in Korea. Here you see the definition. It's a long definition. The more misagreement between the people are, the longer is the definition, and that was also the case here. So we have a quite long definition, which has some very typical keywords here. So flexibility is defined as the extension of possibilities to widen formable product categories to meet diverse demands in lot size, product shape complexity, physical requirements by enhancing the capabilities of forming processes, machines, and forming systems. So this is an overarching definition of flexibility from the group of experts at the CRP, and we all recognize that flexibility in forming plays an essential role in customized, mass, and individualized production in the manufacturing industry. Having said that, we had a second attempt to categorize flexibility in forming, and we end up with 4 basic categories of flexibility. One category in the physics, which is product and process related. Then in the shape complexity of the products, in a degree of freedom which we have available in the tools and in applying the motion to shape the products, and of course the flexibility in the lot size. I'm going to have this talk with a different categorization, which also fits a little bit, of course, our works which we have done at the university. I would like to start with the concept of tool flexibility. So I will give you several examples by which you can generate different products with a very restricted set of tools. Then I would like to present you some work on product flexibility. This aims to show how we can generate different products with the same machineries and the same procedures we have at hand. And as a third point, I would like to show examples on bed size flexibility. So I will show you one process where the aim is to have the bed size 1. So the first part should be the correct part. And then I have the last topic. Hopefully I will have time to touch that topic too, which I called location flexibility. We discuss a lot with my coworkers how to call it. I mean, you can find different words. You can even use the word Industry 4.0 for this. But I like the word location flexibility because it's exactly reflecting the spirit of that kind of work, what we are doing here. So let me start with tool flexibility. The first process I would like to introduce is the process on incremental profile forming. This incremental profile forming process has several actuators by which you can generate different products. And you see the different form of actuation. First of all, you can have a so-called kinematical forming where the tool is rather locally acting, and you may have the so-called form close forming where the tool has a larger contact area and has more restrictions in the geometry you can generate. So the characteristics of this process is the high flexibility, the ideal process for small batch sizes, and of course prototyping. Let us see some pictures of the machine, of the prototype machine we have generated. So you see here the tool holder. There are radial tools, totally 6, and you see each tool, which we call a stylus, how it operates with servo drive and respective bearing here. So those stylus tools are located on a disc, which is rotating itself as well. And furthermore, you can move the workpiece, which you see here in the middle. Maybe I should turn back to my pointer, which you see in the middle, can move axially forth and back. So totally, we have 8 degrees of freedom in this machine. We can see here several examples. The first one where the unilateral tools motion are applied. So we have a single tool and tool which is just opposite to the acting tool, or we have multilateral tools as shown here. In this video on the bottom left, you see the application of tools in radial direction and rotation. So we have forward and backward rotation. Then we have also a motion of the workpiece itself, an axial motion forth and back. On the right video at the bottom, you see the form close action of the process. So we can rotate the workpiece. We have 2 unilateral acting tools by which we can shape our parts. So by that process, we can generate a lot of different tools. We can start with shaping the cross-section uniformly. We can shape the cross-section also variably over the axis of the profile, and we can have also joining through this process in using 2 different parts. The question is, what is the variety of products we can generate with this 8 degree of freedom meshing? So for that purpose, we consider the number of form closed tool axes on the horizontal axis. Then we consider the number of kinematic tool axes on the vertical axis, and have furthermore the axis of basic kinematics. That means radial motion, axial motion, rotation. Those are the red buttons. And we made some very restrictive assumptions. We assumed we have only a circular tube. We have only 2 active tools which are acting. We have symmetric tool order and a single step forming operation. So even with those restrictions, we come up with a huge number of geometries which we can generate. For this number, for these restrictions, we have 108 geometric elements. But if you relax the restrictions which have been mentioned here, you might end up with more than 1,000 different possible geometries you can generate by this tool. So the second example I would like to introduce is the incremental plate forging. And the incremental plate forging is a process. I have to turn back to this initial form picture. You see here the machine. We have a machine designed that has 5 degrees of freedom, 1 axial translation. Then we have a rotation of the tool, which is fixed here on this disc. We have a translation. We have a translation of the workpiece, and sorry. And then we have I had the music of the video. I'm sorry, in my ears. And then we have 2 translations of the tools here. The possible tool motions are stated here. We have translational, rotational tool motions, continuous forming. It's very loud, I'm sorry. So that was not working in the test, now it's working. So I just skipped this. Those are the possible motions. Okay. So I will do the following. I will just remove this. I'm not sure why we have this sounds now. Okay, so I hope the sound is over and I will start again. Yeah, it's playing in the background. So I suggest that I restart my presentation at the point, because this was some. It's still in the background, isn't it? Yeah, but I don't have anything playing in my screen. I'm sorry for that. Okay, so let us try it again. Let us try it again. I'm sorry for this. So. Yeah, okay. So I just move on. Okay. I skipped this slide. So I showed you the machine with the different possibilities of using tools. So what we can do with this plate forging, we can do customized parts made of sheet, which you see here with gears and thickening and similar features in the part. And as an example, we produced a handy casing that there was a visit to our institute from a phone maker from California, and we just wanted to show you them something, and within a few days we end up with this casing made by our Missionary, which you see here with this plate forging, incremental plate forging. And the interesting thing is you can obtain parts which you can only obtain with several processes and a huge effort to reduce the mass in these parts. For instance, if you have gears where the gear part or the teeth part is thicker in order to be able to transmit larger stresses, and the rim part or the web here is thinner. This can be done with this machinery very easily. And we started with the fundamental investigations of that process in the years 2009 to 2016, and the manufacturing of such a gear took about 1,800 seconds. So that was not a very big time, a very convenient time for manufacturing. So we started then after with industrial companies, a project where we try to reduce this manufacturing time to acceptable limits, and we end up with production times of less than 40 seconds by changing the kinematics of the tools, by increasing the speed of the machine and things like that. So what I would like to show you here, our basic work is usually in the fundamental investigation, and we do not care so much about the economics of the process, but this is something which we can pursue as soon as we have the interest of the industry. So the next issue is product flexibility, and for that I would like to start with products that have special features like this electric connector. So electric connectors have a body which is made of light metal, and then they have a portion where you have a high electric conductivity. This is copper in that case, and you achieve this by electroplating on aluminum, and it's an extra process you have to do. Another application of features you want to have in parts is, for instance, this power shaft of a tractor. You might have a region where you have corrosion resistance at the surface. You might have a part of the shaft where you have a high hardness, and another part where you have to have an even higher hardness. And in order to produce such parts, we introduced the draw forging process, which is a combination of deep drawing and forging. So you see here the process. We have the sheet, which is shown in blue as the blank. We have the deep drawing tools, and we have the extrusion tools at the bottom. The first tool for deep drawing is the core of the product, which is shown here. So it will deform during extrusion. And then we have the punch of our machine. So in the first step, we have the deep drawing operation where we generate our cup with the core as the punch. And then we have redrawing and forging. So we redraw the cup into a smaller cup, and at the same time start the extrusion of the process, of the inner part. In that way, we end up with products. You see here the experimental work, the blank, which is stainless steel, and the aluminum core, which is surface treated. And after the deep forging, we end up with our aluminum exudate with a covered shell at the tip of the product. So we can cover the shell not only at the tip, we can cover it all over the product. So you see here the aluminum core, and over this core we have all the way through the shell covered. And if we make a cut, you see here the steel shell with different hardness, of course, as the aluminum, and with also different thicknesses, which we can partly control in the process. And you see here a clearance, which is because of the form closed joining of the part. You have a spring back here. We don't get material bonding. We get either force close or form close bonding in general. If you use two aluminum sheets, cores and sheet, then it's possible also to have material bonding. So we can do something else. We can use a pierce blank, and with that pierce blank, we can achieve different sheets on different parts of the shaft. So this is steel blank 1, has a different property, then steel blank 2 has a different property. It doesn't need to be even steel, it could be any other material, and then the aluminum core. Okay, Another example for flexible products is the incremental tube forming. The incremental tube forming is a process which has been generated through completely physical considerations. We wanted to reduce the stresses in the bending process. So we do that by superposing to the bending through spinning stresses. So those are the 3 spinning rolls, and they spin slightly the diameter to a reduced diameter, and by that simultaneously we bend, and through that we have a completely different stress state. So here you see the machinery which is produced by a commercial company that acquired the license for that process. Through this process we can generate complicated profiles as shown in the system with different geometries. The process itself has 2 advantages. The first advantage is that we can reduce the moment by a factor of up to 35 times, and that can be seen here. So the bending moment relative to the moment where we don't have the spinning is shown here. We can reduce it to 2.5% of the initial bending moment, and that means we have much less spring back in this process, exactly by the same amount, because it's more or less linear to the moment, and in that way we can increase the quality of the product. But that's not the only one. The second important feature is that we can use the spinning and change the cross-section during bending as well. And you see here several examples how we have done that for this purpose. The nice thing is, due to this reduction of the bending moment, we were able to bend difficult to form metals like titanium at room temperature with this machinery as if it is an aluminum profile. Okay, another example is to use additive manufacturing to produce sandwich sheets, which have the property of having multi-material at the first hand, have different cross-sections, have a structure in them to generate lightweight products, and allow us to have sensors and, for instance, cooling channels. So those parts are produced in flat sheets by additive manufacturing, and then they are formed. So the question is here, why don't you, so that would be the formed part, why don't you additively manufacture the formed part directly? The question is time and energy. So we are able to produce flat geometries through the additive manufacturing, and then use the metal forming process to generate parts which have large surfaces and large volumes with a lot of free space in them, so typical shell structures, and manufacturing of those cell structures by additive manufacturing takes a lot of time. So this is one point which we achieve through this process. So here you see a bending operation of this structure and the grace which is coming out of the part. Now, I would like to shift to the bedside's flexibility. My time is running out, unfortunately, because of this noise in the video. So we started 5 minutes early. Oh, that's great. So I can continue then. Thank you. So the next topic is the bedside flexibility. And for that, I'm going to start with this torque superposed spatial profile bending. The aim of this process was to produce parts in the bed size of 1. So the first part should be a part with the correct spring back, with the correct dimensions and geometry and so on. For this purpose, we generated a multi-degree of freedom bending machine in which the profile is transported through the rollers, and then the head can move in the bending direction by translation as shown here. as shown here. And then it can rotate in 2 directions in order to apply twisting moments, so that we have a very strong control of the bending process during this action here. And this has been manufactured, this machine has been manufactured by a commercial company who got the license for that process, and is now available also in a much nicer form. Our own machine is not so well designed. But anyway, what we can do with this machinery now is to produce complicatedly bent parts in different planes, in different dimensions, and those parts have exactly the geometry we require. So the spring back compensation and everything is done for the first part in the machine by the control we have available. Okay, the next example, and I will skip that a little bit quickly, is the combination of additive, subtractive, and formative deformation manufacturing in a single machinery. So we started that with the DGM Mori laser tech, which can do machining and additive manufacturing. We added to that the single point incremental forming feature, so we can form sheets in that machine, and at the same time in the same machine add the side features which we would like to have, and then machine those side features in the same machinery. So that gives us a large flexibility in the manufacturing and in the product we would like to have. This is also for small batch sizes or even prototyping, but the nice thing is we can combine large volume manufacturing by single point forming with the small batch features of the additive manufacturing. So I'm coming now to the location flexibility, and that's the last point. The location flexibility was initiated at our institute through the wish to have labs which are shareable between colleagues. And we started a very early project, European project, even with our colleagues in Stockholm. They were participating there. And then widen that out to manufacturing processes as well. So the first idea was to have a lab, which you see here, with different testing machines. This is a Zwick Bub, which does some sheet forming processes, a simple tension or compression machine, and the robot, and we have different magazines to feed those machines. So this is connected by a web server to an interface where you have up to 5 cameras by which you can observe the test, and by which the user can actively change the setup of the machines. So by doing that, we have I hope that the sound is not too loud. So what you see here is that the user tells the machine which part the robot should put in the testing machine. Then the testing machine is fed by the part, and during the test you get online the force displacement curve or the strain measurement if you have a transducer in there, and can observe the cracking geometry and take out the part, and with the camera you have on the robot you can watch the respective part. The same you can do with the deep drawing process, so the students can assess the pressure, the depth of the cup, and then you can have various tests. So this is a test where the cup is relatively okay, and if you select the wrong pressure, you might get a part where you have a fracture like that, or you may get, if you have too less pressure, a part where you have wrinkling. So in this way, the students are able in different countries at the same time to make tests with drawing depth and blank holder and determine the process window for a given steel for this process. So this is one application. That was all for the lab purpose, for the lecture purpose. Now we extend that and went over to the tube bending cell. So we have now the tube bending cell at our institute, which is also now remote accessible from all over the world. So currently we have more than 20 countries which access to our lab through those telemetric possibilities and can conduct experiments. Now this is can be a production unit or an experiment for the lab, and you can watch whether the part is okay or not and correct the parameters in the next run and so on. So that was the final slide which I wanted to show you. I thank you very much for your attention, and please forgive me for the problem with the sound. It was unexpected. Thank you very much for your attention.
So thank you so much,
yes.
Dr. Tekkaya, and I think it was very interesting to see you, and thank you for an exciting review of all the different aspects of flexibility. And now it's some time to open for questions. So please now put your questions in the chat, and Robin will send them on to me in a short while. But of course, I have some questions already. And you talked about the challenges with electrification that many companies now are facing. And in all these four aspects, what part of the flexibility do you think will be most important now? Is it a lot size, or is it actually the physical, the shape of the material?
I think it's the diversity of the components. That's coming more and more. So the questions we get from industry are basically on the diversity. So if you think about a typical car, either a Volvo or a BMW, you have millions and millions of options in that car to order. And this will not change with the electrical cars. It will get even more. So you have a huge branch of different product types which only minorly differ, and metal forming is not good for such kind of products. So we have to adapt our processes to enable them to have slight changes in the geometries, maybe even also larger changes, but basically slight changes which can be done with the same tools, with the same machinery, and with the same processes we have at hand.
And
that's the biggest challenge, I think. Yeah.
Thank you very much. And there you really showed also how with just one machine you can make thousands of components.
Yeah.
And we just have comments from very great presentations.
Thank you very much.
Thank you from the audience here. And also, I would like to ask you, you said that you have impact also already in industry, because some industries have already taken your innovation and created their own machines. And I also saw DG Mori now, this new process. Do you think that will also happen in that machine with forming and additive manufacturing and machining together?
Yes, I mean, the machine was already provided by DG Mori, which can do the machining and the additive manufacturing. So what we have added to that was the ability to do also the incremental forming, sheet forming, and so
now we have some double.
Yes.
Yeah.
So I'm still speaking without speaking. Okay, now, so I think that can be done with any of those machines easily. So if you have such a machine, you can change your control system and then start to do incremental forming as well. And I think that's a very attractive process to do. We use this machine also for another process. We have currently another process running on that. I mean, additive manufacturing is in all the discussions, and people see a very big hype in that. No one is talking about the CO2 footprint of additive manufacturing. It's catastrophic. It's almost 10 times more than metal forming, and you have to take care about that. And what we are doing now is we change to the system with the same machine we have, not to additively form powder, but to additively form sheets. So we bring sheets together. You don't have to cast or melt a lot of powder. You just have sheets which are coming from the rolling plant, and then bring them together, and then use additive manufacturing to connect those sheets to products. And in that way, you have a fantastic CO2 footprint of this process, and don't have this problem of steadily melting and cooling and melting and cooling and blowing CO2 in the atmosphere.
So I think that's a very important part, because we also saw how much AI is now discussed with respect to CO2. But I look so much forward to the Q&A session later on.
Yeah.
And thank you very much, Dr. Tekkaya. And
Thank you
now
very
we
much,
actually, thank you again.